Recently, our solar system received a messenger from the depths of the Milky Way, sparking an unprecedented observation effort that has crossed the boundaries of global space agencies. This visitor is none other than the interstellar comet 3I/Atlas, and its cosmic ballet has brought it perilously close to Mars, offering an extraordinary opportunity for study. Following the historic initial image capture by NASA's Perseverance rover, the European Space Agency (ESA) sprang into action with its sophisticated spacecraft currently orbiting the Red Planet, transforming Mars surveillance into an outpost of interstellar astronomy. The rarity and speed of these objects, which are not gravitationally bound to our Sun, make each observation a scientific treasure. Seeing 3I/Atlas streaking across the Martian sky is not only a visual curiosity, but a chance to capture fragments of matter formed in an entirely different star system. This collaborative effort, combining surface-based rovers and orbiting satellites, demonstrates the complexity and dedication of modern science in unlocking the secrets of these celestial aliens, which have traveled incalculable distances for millennia, bearing a unique record of the distant universe. The hunt for 3I/Atlas was a true interplanetary team effort, orchestrated to capture as much data as possible as the comet flew past Mars. The key moment for ESA's observations occurred between October 1st and 7th, when the ExoMars Trace Gas Orbiter, TGO, and Mars Express satellites were reassigned from their routine atmospheric and surface mapping of the planet to become comet hunters. ESA teams turned their powerful cameras into deep space in search of this cosmic alien, which was an incredible 30 million kilometers away at the time of the capture. This astronomical distance underscores the technical feat involved, as it means the captured image represents the interstellar object within the context of Martian orbit. Coordinating the simultaneous reorientation of multiple orbiters toward such a tiny, fleeting target is complex, requiring extremely precise orbital calculations and impeccable timing. The data collected, despite the inherent challenges of distance, promises to provide the best view ever obtained of such an active interstellar object in its close passage. The main obstacle for ESA was not only the distance, but the very design of its instruments. The cameras on board TGO and Mars Express were meticulously calibrated and engineered over years for a single purpose: to clearly record fine details of the surface and thin atmosphere of Mars, objects that lie only a few hundred kilometers from their lenses. Changing this perspective to observe something so small, infinitely more distant, and inherently dim was, therefore, a colossal technical challenge. It was like asking a landscape photographer to suddenly photograph a bee from 5 kilometers away. The faint light reflected by 3I/Atlas, combined with its relative speed and the need for long exposures to capture its ghostly light, required mission operators to make radical adjustments to imaging parameters, testing the sensitivity limits of the instruments. The ability to image the interstellar comet under these conditions demonstrates the flexibility and latent potential of Mars orbiters beyond their primary planetary exploration missions. Among the instruments used, the CASIS Color and Stereo Surface Imaging System, aboard ExoMars TGO, stood out for its remarkable adjustment capabilities. This instrument managed to capture a vital sequence of photographs that confirmed the location and passage of Comet 3I/Atlas. The visual result, while technically complex, is revealing. The images show a tiny white dot moving slowly across the star field. This faint dot, however, carries an enormous wealth of scientific information. It represents the most concentrated and brightest portion of the comet, its icy, rocky nucleus enveloped in a diffuse cloud of gas and dust known as the coma, or popularly nicknamed the coma. It was this diffuse cloud, not the solid nucleus, that CASIS was able to illuminate. TGO's success in capturing this cosmic signature confirms the effectiveness of long, controlled exposures, ensuring that even the faintest and most distant objects could leave their mark on ESA's sensors. The nucleus of Comet 3I/Atlas has an estimated diameter of only about a kilometer, a surprisingly small size for an object traveling through star systems. This small scale, combined with the tens of millions of kilometers away from ESA's cameras, made the comet's rocky, solid nucleus unreachable for imaging equipment. ESA used a striking analogy to illustrate the challenge. Distinguishing the nucleus would be as difficult as trying to see a cell phone left on the surface of the Moon with the naked eye from Earth. This comparison highlights the astronomical scale involved. However, the diffuse glow of the coma is what saves the observation. The coma is a gigantic cloud of gas and dust that can extend for thousands of kilometers, enveloping the nucleus and acting as a beacon that reflects sunlight, allowing ESA to detect the comet even from such a colossal distance. Therefore, although we cannot see the central rock, we are seeing the trace of its interaction with the Sun, a vital signature of its composition. The formation of a coma is a dynamic and fascinating process, fundamental to the classification and study of comets. The phenomenon begins when the interstellar object approaches the Sun. The increase in heat causes the sublimation, the direct transition from a solid to a gaseous state of volatile ices, such as frozen water and carbon dioxide, contained in the rocky nucleus. This release of gases and dust creates the luminous halo, or coma, which can expand vastly. In many comets, this cloud gives rise to a long, iconic tail, which is always pushed away from the Sun by radiation pressure and the solar wind. In the images captured by Cassis, the tail was not yet clearly visible, indicating that 3I/Atlas was still relatively distant and experiencing low outgassing activity. However, scientists' expectations are high. As the comet inevitably approaches the Sun, sublimation activity will dramatically intensify, and the tail should form and become an observable spectacle, revealing more about the object's trajectory and behavior. TGO's success, unfortunately, was not initially replicated by the other spacecraft involved, Mars Express. Its half-second exposures proved too short to capture the faint light of such a distant and faint object, while TGO used exposures up to 5 times longer. This technical setback forced scientists to go back to the drawing board. Currently, an intense effort is underway to combine and adjust the images recorded by Mars Express, using digital processing techniques to try to increase contrast and, perhaps, reveal the comet that was hidden by the short exposure time. However, the most important and potentially most fruitful work lies in analyzing data from the spectrometers on both spacecraft. These vital instruments measure the specific type of light reflected by cosmic objects. By studying the 3I/Atlas spectrum, scientists hope to identify the chemical signature of the gaseous elements and dust that make up the coma and potential tail. This is a crucial step in deciphering the comet's chemical composition, offering clues about the environment of its star system of origin. Comet 3I/Atlas holds a remarkable status. It is only the third interstellar object formally observed by humanity, following the mysterious Oumuamua, 2017, and the more classic 2I/Borisov, 2019. These cosmic bodies are essentially time capsules and intergalactic messengers, having originated in alien star systems and been flung into our solar system by extreme gravitational forces. They bring with them unprecedented clues about the formation processes of planets and stars in distant, unexplored regions of the Milky Way, offering a sample of materials we could never otherwise access. Analyzing their composition is equivalent to cosmic forensic. According to ESA scientist Colin Wilson, it is extremely exciting to see our orbiters, which are normally dedicated to studying Mars in detail, reacting to unexpected events like this and proving their versatility. The ability to quickly repurpose these assets to study these rare visitors underscores the maturity of Mars missions and the profound impact these studies will have on our understanding of galactic ecology and the formation of neighboring solar systems. The influx of data and the success of the 3I/Atlas observations solidify the need for missions dedicated to capturing these rare phenomena. Therefore, ESA is preparing the innovative Comet Interceptor mission, scheduled for launch in 2029. This is a space observatory designed to wait, at a strategic point, for a primitive comet, or, ideally, another interstellar object, to pass close enough to be intercepted by one of the mission's secondary probes. Michael Kupers, project scientist, recalls that when the mission was conceived in 2019, only one interstellar object was known. Today, the frequency of discoveries already shows that there are more of them, and that they are very different from each other, reinforcing the mission's urgency. Intercepting and closely studying one of these bodies could offer us the key to understanding their origin and nature, answering fundamental questions about the primordial matter that makes up our galaxy. Even if the mission doesn't encounter an interstellar visitor immediately, it will serve as a vital testbed for future rapid response operations, ensuring that humanity is prepared to study these cosmic fragments that continue to traverse our star system.